So I'm sorry, we're going to talk about calculating the center of mass. So to do that, there are a set of steps you have to do. And I'm going to try and be very clear about what these steps are. And if you look this up in the book will do this different. But I also want to let us know we're going to do a solid, regular rod or stick or whatever you want to call this, something that has some kind of uniform symmetry. And more importantly, we know that the center of mass of this is at its middle. We know the answer. So we're solving for something where we know what the answer is going to be already. But we're going to try and show how it's done. So this is more a set of process as opposed to the expected answer. Let's set up some information here. Let's first indicate that the entire thing has mass m and that it has length L. We're going to try and determine what its center of mass is. Alex, can you turn out one of the gray lights or both of the gray lights? Because nobody can see that TV in the back. All right, that'll do. Thank you. So there's a couple places that we have to begin. And I want to start by reminding us that this is always going to be the mass of the object. Generally, we tend to know that. Meaning we tend to say, okay, the mass is m, so we just put m for the denominator. But there are occasions, and you guys in E&M, you know about these occasions, where you won't know the mass of the object, where they'll give you the density and its shape, and you have to derive the mass of the object. That's not implausible, but that's why that's in the denominator. This idea that you might not know what the mass is, you might just know information about its shape. But let's assume for the time being that we're going to deal with a situation where we know the mass. So the denominator will just be the mass of the object. So we're really focused on the numerator here. Now, before we launch into these problems, you have to look at the object and decide whether this object really fits one of three molds. Is it a one-dimensional object, a two-dimensional object, or a three-dimensional object? And trust me when I say that sounds ridiculous, but a meter stick, which this is modeling a meter stick, do you really have to treat it as a three-dimensional object? I mean, it's got a lot of symmetry. So I think because it's so very long compared to its other measurements, it's not too weird to treat it like a one-dimensional object. Trust me, one-dimensional is easier. So if you believe you have enough symmetry where you can do your problem in one dimension, you should do so. And if you can't, try and get it to 2 dimensions, not 3. 3 dimensions will be hard. Every dimension you add is another integral. And those integrals could be connected together. So you could be looking at having to do 3 integrals that are all connected together. We want to try and avoid that. So if you can, always try to go to the least number of dimensions. I think that we could treat this as a one-dimensional object. So if you can figure that out, if you have a way of doing that, then try and whittle it down to something as least multidimensional as possible. Now, if this were a disk, I probably couldn't do that. I'd probably have to treat it as 2 dimensions. But I would try not to treat it as 3-dimensional. Like if it was a CD, I'd say, well, it's very thin compared to its surface area. I'm going to try and treat it as a 2-dimensional object. Does that make sense? We're going to treat this as a 1-dimensional object. So once we have decided that, the first thing you should do is establish its density. There's 3 different kinds of densities, but all densities are mass per unit shape if we're dealing with mass density. It's a ratio. It's something about the property of the object divided by its shape. So if we're talking about a 2-dimensional object, it'd be mass per unit area. And obviously a 3-dimensional object, that'd be mass per unit volume. Generally, we use lowercase Greek l, lambda, for linear density. So if it's a guitar string, that would make sense. Linear density. Meter stick makes sense. Linear density. Now, the next part we have to do, this is where it starts to get more complicated. And this is why when we start doing this problem, we want to start for something that has, some simple symmetry. To actually calculate this, what we have to be able to do is we have to describe each piece of this object and its relevant information. If we look at this integral is telling us to find a piece of the object. That's what dm means. Find a piece of mass. Figure out how far away it is. I didn't say from where, just figure out how far away it is, which means we also have to establish a reference point. And then add up every piece until you have the entire thing. That's what those 3 things tell us to do. So the first thing I'm going to do is identify a piece of the mass of the object. Now I do that in kind of a ridiculous manner. I physically draw a little square on the object somewhere and fill it in. That's how I've always done it. I pick a place on the object and I say, this is my piece. And I don't know what it is, how big it is, but I'm going to call it dm. It's a little piece of mass. Can't say that without the m, without having problems. So we just say a little piece of mass. But now that I'm saying it over and over again, think about that. Can't drop the m. Is that subtext coming through? Because then it'd be a little piece of something that's not as good to say in school. That's right. So a little piece of mass. I think I'm hearing the brewing of a new physics shirt. It's a nice piece of mass you got there.
That was funny.
It would be. Probably would have to have a conversation with my principal. But I say, beg forgiveness. Don't ask permission. That's right. It is a great motto. So I heard about a party this last weekend where the police might have been there, and one of the kids at the party was in one of my classes indicating that he had to say something similar to that to the police officer. It started with an, I'm sorry. I guess it was better to beg forgiveness than to ask permission. All right, so we have to define our piece of object. So I'm defining it by saying I have a little piece of mass right there. Now, the next part is we have to figure out how to tell our problem where that piece is. Now, that usually requires that we pick a reference point, because in this case, it's a distance. It's a one-dimensional object. So I'm going to choose reference. I'm going to say here. This is where I'm going to begin. And I'm going to say that there is a distance from my reference to where my object is. I'm purposefully not using R. I'm choosing to use X. R is a pretty loaded term. We tend to think of it as radius a lot. But X is horizontal, right? The X axis, the X coordinate. So it feels more natural, since we're dealing with a linear object that's already horizontal, to use X. If it were vertical, I'd probably use Y. So I want to be able to point to where this object is. And I want to use something that we all agree on. So if I tell you it is X distance away from the origin, and I say the origin is the left-hand side of the object, we can all agree exactly on where that is now. And it also helps me figure out something else. Because remember, I have to add up every piece of the mass. So because of that, can I figure out where this mass begins and where it ends? I think I can. I've kind of indicated that the first piece of mass will be located at 0, and the last piece of mass will be located at L. So that's a nice big piece of mass. Get it? Mm-hmm. I'm sorry, I'm going to have to keep doing that all class period long. Except for those people at home, because if the M's don't come through and it's like cutting in and out, those parents might be frustrated. Yeah, it's going to be bad. I'm going to get phone calls. All right, so again, step 1, identify what a mass is. Step 2, you have to find a way to point to it, something that we can agree upon, that we can use to describe every single piece of mass. And the next part's where a lot of students have difficulty, but it's actually one of the easier parts. We need to describe the size of the mass in terms of the shape. But that's always going to be done the same way. And that's because we have density. I already have a way of doing this. I chose to come up with a way of describing the density early so that I can say that the mass, the piece of mass, is going to be equal to the density times how big this piece is. This piece is a little bit more than X. It's a little width of mass. This allows me to describe not just where the mass is, but how big that mass is using the same term, X. Now, of course, if this was an area, I'd probably have a dx and a dy. And I'd have to multiply those together to get an area. If this were a volume, I'd probably have a dx, a dy, and a dz, and I'd get a volume. You can see why that would be, more complicated if I have area and volume. So it's nice when it's something simple like this. But what this allows me to have is a new way of talking about the shape of this object. I can describe it in terms of its density, but I can also now describe it in terms of its shape. It's a length, and each piece of length can contribute to the whole mass. So the first step was to identify where my mass is. My second step was to find a way to point to it. My third step was to find a way to address where the beginning is and where the end is. And then I needed to convert dm into something related to its shape, dx. Now that I've done that, I'm going to assemble the integral. Now, this is the part I think that's hard because a lot of you don't understand what this is, but these are just symbols. It's symbology. So let's be very careful. We are assembling our own, but this is the framework that we've been given to assemble it under. The dm is just a placeholder that tells me it's a piece of mass. That's all it is. We are going to replace it with something that has to do with the density and the width of each piece. R is my pointer. It points to where the object is, where this piece of mass is. And it assumes that we've picked a reference point. For us, that's x. The integral is a mathematical construct. It's like the times sign or the divide sign. It's just more complicated. As you got into more complicated math, we have more complicated constructs. So that's what it is. And this construct is a sum. It's telling us to add. But it's telling us to add using some fancier math. However, this construct requires input. It requires some more symbology for us to tell the math where to begin our addition and where to end our addition. Those are the limits. So we're going to tell it to start at 0 and end at L. So we have constructed our integral. We took all the time necessary to find out what each of these pieces were. And now that we've done that, we have constructed the integral. Now, the actual execution of the integral has nothing to do with center of mass. The execution of the integral is something you learn how to do in your math class. It does the summing for you. Meaning, I don't have to know why we do it this way to know that the end result will be the sum. It will add up all the pieces for me. You're going to learn a variety of ways to do this. But ultimately, this symbology means something different once the integral is constructed. Meaning, once I've spent all the time figuring out all the parts to my integral, I'm going to resort it and remind you that this tells me that I'm going to integrate. This is what I'm going to integrate. And this is with respect to which variable. So although each of those had a different meaning a moment ago, when I go to do the calculus, the actual summing part, these all now have a different meaning. Read from the backwards, I'm going to, with respect to x, meaning I'm going to look at my expression, and x is the important variable, and everything else is a constant. I'm going to integrate, which means I'm going to sum by doing the antiderivative of this expression. And after I get the antiderivative, I'm going to apply the limits that tell me where to start and stop. This is a mathematical thing. So the actual integration part, you will learn all sorts of different techniques. The first thing I'll tell you is if there's a constant, get it out of there. So the first thing we should do is get the constants and pull them outside. They're not part of the problem. Next, you should have an expression here. To take the integral requires that we take the antiderivative with respect to our featured variable, with respect to x. That means x becomes the variable. Now, you're going to learn a lot of stuff. If it was there was trig functions in there, you'd have to do something with trig. If it's a polynomial, you'll do the polynomial. As you learn more things, you'll learn how to do other stuff like U sub or integration by parts or Lagrangian transformation. There's all sorts of stuff you can do. You'll learn a handful of skills. But when you're actually doing this for your job, you'll just open up the book and look at the answer. You'll type it into Wolfram Alpha. You don't do this by hand anymore. Nobody does. You do it by hand in your math class, the same way you don't do, longhand division anymore. Are you really breaking out your little thing and looking at your remainders anymore? Same thing. That's exactly what this is like. So you'll have a machine do it. Now for us, we don't get that option, so we have to do the calculus. And I'll remind you that this is x to the 1. So we're going to find the antiderivative by adding 1 to that exponent. Then we're going to divide by the new exponent. Put it out front. There, we've done the antiderivative. That's it. That's the only part that your whole calculus class boils down to that. That's not exactly true. There's a lot of tricks you have to learn between now and then. We also have the fact that we have to employ our limits. So notice I take my antiderivative and I put it in brackets to remind me that I have to deploy my limits, but I don't forget the fact that I have this thing I pulled out in front, these constants. Now to complete the math, I do have to employ my limits. And that's going to give me 1/2 lambda L squared minus 0. So I have now finished the calculus portion. And I'm left with this. This is the answer. That's not the center of mass. That's just the answer to the top portion of the center of mass. Any questions about that so far? I've taken 3 breaks during the conversation to make fun of, talking about mass. That was to try and break up some of the pieces here so it wouldn't be so terrible. But we started with setting up our system and ended now with 1/2 lambda L squared. We're not quite done, but I think the hard parts are done. Because the next part is just doing this fraction. The actual x center of mass has me put 1/2 lambda L squared in the numerator and mass in the denominator. Right, the center of mass has a numerator and a denominator. I have to make sure I put both parts there. Now, that's not the way we should leave it because we created the lambda. We used it as our placeholder for density. But now that we're done, we need to put that back in, which gives me 1/2 m over L times L squared, all divided by m. And of course, this isn't a surprise. It's 1/2 L. We knew the answer from the beginning. But now I should be able to give you any shape. And if you can figure out how to express it, you should be able to figure out center of mass. Also, the only difference between this and moment of inertia is it wouldn't have been x, it would have been x squared from 0 to L. You do this, you would have gotten a moment of inertia of the system. So if you can do one, you can do both. Every other step is exactly the same. So that's why it's good to have some practice, good to have a place to start. Okay. Yes, ma'am.
When you're picking, oh my God, sorry. When you're picking your piece of mass, do you want to pick it around where you think that it's going to be, like around where you're predicting the center of mass is going to be?
No, I just picked a random square in the middle.
So it's just arbitrary?
Yeah, I could have just as easily said, I just drew it somewhere. I wanted to draw it so it'd be big enough where I was indicating I'm in the middle of it somewhere. But it, that part doesn't matter. Okay. In fact, a lot of the folks have been in, in E&M and have seen that, we've had to do like discs and stuff already. So I will pick a block, somewhere in the middle. Okay. Just I need a spot. I need something I can use. So we will do 2-dimensional integrals second semester because we will have to find the moment of inertia of discs and balls and stuff like that. And I intend for us to see all of them done because I think it's a good mathematical exercise. Mm-hmm. But also it'll show you some interesting things that might happen in the exam. So That's all I really want to talk about when it comes to center of mass. The big reminder for you guys, though, you throw something in the air, it's going to naturally rotate about its center of mass. I keep emphasizing that because it's been on the exam. You need to be aware of that. That if you don't have a pivot point and something's going to be spinning, assume it's a center of mass. So if you have something that's on a sheet of ice and they kind of just throw it, it's going to naturally rotate about its center of mass. If you have a bar on the ice and a object runs into it, they're going to collide, but this object here, it's going to go away spinning, but it's going to spin about its center of mass. They don't have to tell you that on the exam. You have to know it. So with that being said, though, we're going to move away from center of mass and definitely away from energy. And we're going to talk about momentum now. And it should make you happy to know that this is the last topic of first semester. When we've covered momentum, we have finished first semester physics. Not that that means anything. There's not an exam anymore for the end of first semester physics, but it does mean that there'll be only 3 topics left second semester. Although one of them is big. Angular momentum, angular energy, that's a big topic. It's got a lot of facets. Torque, all of that. It's basically everything we did first semester, but for things that rotate. The nice thing is it's all the exact same stuff as first semester, except for things that rotate. So you've already learned it all. We just have to apply to things that rotate. Then we're going to talk about oscillatory motion. That's about a week. It's really short. It's not a whole lot of stuff. But then I've saved gravity for the end. So we're going to do gravity, orbits, Kepler's laws at the end. And that'll be what we'll be doing that in March, probably either right after spring break or part of it before spring break and part of it after spring break. So it really depends on how long we want to take to do rotational motion and angular momentum. I would expect that you guys would want to stretch that out a little bit. It can be quite challenging. And for those of you who've had a little bit of it last year, you know that, it really dresses stuff up. It changes things quite a bit. So, but today, momentum. And this is really targeting those people who have never had physics before, because I always like to introduce the topics. I want to start by saying that momentum is a seminal topic in physics. It is probably the most important topic in physics. When I say that, I don't say that lightly, because you've heard me say that this is a very important topic before, but all of Newton's rules were actually based on momentum. They were not based on acceleration. In fact, his derivation of Newton's laws are all in terms of momentum. They're not in terms of acceleration and mass, because he believed that momentum was a more powerful concept. Momentum is a true measure of an object's inertia while moving. Mass isn't a good measure of an object's inertia. I want you to think for a moment about a bullet. Bullet's just a piece of lead. It's light, a couple of grams. Changing its momentum is no big deal. But if it's traveling 1,000 meters per second, changing its momentum is a big deal. It's much harder. And it's important that you understand that the faster something goes, the more difficult it is to change. That is what inertia and momentum are truly meant to express. That velocity plays a key and pivotal role in determining how difficult it is to change an object's motion. So Newton really began here. In fact, when you look at his expression for Newton's second law, it's a more complicated vector equation because it's the rate of change of momentum is how he expressed his second law. And you can kind of see where he came with this. We teach this differently because we're dealing with high school students, so this is their first time through it, but also Newton didn't think you guys were worthy of even learning it. So when we start by looking at what we teach, you can see why we teach it the way we do. Motion's easier to see. We can do some stuff with motion. Accelerations are easy to measure, and we can see how things velocity change. It's harder to see inertia. But we know from motion equations that we probably could derive momentum directly from these equations. I mean, it doesn't take much to realize that momentum has been built into this the whole time. So I hope you're seeing this because it's a part of what we've been doing the whole time. All right, you see it there? Now, there's a little more I want to say before we really start talking about this. So let me make sure that all of you have an understanding of the units here. The units of momentum, kilogram meter per second. It has no special name. I mean, you're welcome to refer to it as the Sheltie, but probably not a good idea on the exam. So kilogram meter per second, there is no special name for it. And it's, there's nothing unique about it except that it has one of each of our major units, kilogram, meter, and second. But there's a couple of things that have the same units, but they're all named different things. So the kilogram meter per second is going to come up a couple of times. And it starts by talking about this. So before I flip to the next page, let me just remind you, momentum is a vector. It has direction. In fact, it's distinctly a vector, and it's important to recognize that it is a vector. It is distinct and different from kinetic energy. These do not measure the same thing, and one is not the derivative of the other. So please don't get that into your mind. It doesn't work that way. And it doesn't work that way specifically because kinetic energy has no direction. It has a bigger emphasis on velocity and less emphasis on the mass. Momentum is about direction. In fact, it's important to note that one of the important differences between energy and momentum is that momentum carries the information of direction with it, because momentum is going to have with it a very strong conservation rule. And for those of you who've been through physics, understand that there is conservation of momentum, and it is a more powerful conservation rule than energy. Because with energy, there's always seems to be some other form of energy coming out of the woodwork. But there is only mv for momentum. Once you know the momentum of the system, you understand that momentum is a conserved quantity. Now, what I wish to speak about is taking this thing we have right here and multiplying both sides of the equation by t, because this is really what momentum is about. When I do that, I get the left side, which is net force times t, and the right side, which is delta p. And I'm writing it specifically with that gap in the middle because we have a name for this called impulse. Impulse is both sides of this relationship. If work was how you change something's energy, impulse is how you change something's momentum. It is the other side of that coin. You can be doing work and applying an impulse at the same time, sure, because you can change something's energy and its momentum at the same time. But the quantity is different. Impulse has two sides. It has a causal side and an effect side. There's several distinctions here that I want to be very clear about. That impulse probably doesn't imply what you think it implies. I want you to consider two cases where the impulse is the same. I have a wine glass, I drop it on a tiled floor. I take a similar wine glass, but drop it on a carpeted floor. If they're both dropped from the same height, they will both acquire the same momentum by the time they make it to the ground. Does that make sense? They'll both have the same velocity. The ground is going to stop both of them, which means the ground is going to apply the same impulse to both glasses. Of course, the glass is probably going to shatter here, but it's probably going to be fine here. The impulse was the same. In both cases, the glass was brought to rest. Therefore, the impulse on both glasses was the same. The result was different. And that's because of the cause. The tile floor applied the same impulse to the glass as the carpeted floor. But the tile floor stopped the glass sooner. But to do so, it had to apply a greater force. It was force that broke the glass, not the impulse. Some of you have been in a car accident before. We have made great strides to make cars safer. But in all cases, cars make you safer by increasing the time it takes for the accident to occur. More importantly, increasing the time it takes for the impulse to be applied to you. No matter what happens in your car accident, you're going to be brought to rest as a result of the car accident. That can happen very fast or very slow. It's very likely you would prefer it to happen slowly, because the slower it occurs, the less force that will be required for you to be stopped. That's the heart of understanding impulse. I don't want to be stopped by the pillowy softness of the dashboard. I want to be stopped by a combination of the crumple zones in the car, beginning the process of stopping first. And then I want the airbag, and then the seatbelt, and last result, the dash, but by then I should be going really slow. Otherwise, you stop by the dash all at once. How soft is your dash? Now, when we talk about cause and effect, it's important to understand that impulse is just the change. It doesn't tell you how that change is made. It's just the change. Somebody throws a punch at you, you don't lean into it. That's going to stop their fist faster. Their fist is going to stop either way. The best way is have them stop their own fist, and then you don't get touched at all. But anybody who's been in a fight knows you're going to take a hit. You're going to take some hits. That's a fight. Learn how to take them. Lean back. Let them go ahead and get that energy out. That way you can control the fight better. Every boxer knows this. Now, when we talk about cause and effect, there's several features here that I need to make sure I impart to you. Impulse is measured in the same units as momentum. But impulse isn't momentum. It's the change in momentum. That's important because impulse is in the direction of the applied force. It is not in the direction of either of the individual momentums. It's not. It's in the direction of the change in momentum. So be very clear that this is a different direction than either of these. All right, if I hit a baseball, I've clearly changed the direction of the baseball. The impulse will be in the direction of the force I apply to the baseball, not in the individual momentums of the baseball. So the direction of an impulse is in the direction of the net force. This will also be the direction of the acceleration of the object. All right. That's a lot for one day. That's about as far as I want to get. So we will continue this tomorrow. Are there any questions? This is mostly review. So students who had this last year understand a lot of these pieces were already presented. All right, we'll talk a little bit more about this tomorrow, but tomorrow is going to be first FRQ, then we're going to do some demonstrations, some laboratory-like activities, and we're going to talk about impulse and collisions. So that's tomorrow. Any questions from you guys at home?
Gonna go over the homework.
Say that one more time because I couldn't hear you.
Are we gonna go over the homework?
My plan is to go over the homework on Friday. Is that okay?
Yeah.
If you have a question on the homework though, and it's pertinent to what you think is going to be on the practice, or I'm sorry, the FRQ tomorrow, I would be happy to answer a question or two before class.
I don't think so. It's
Okay.
number 9. Like that was the only one that was confusing, but it had calculus in it and all the others didn't.
All right, I'll look at number 9 because I don't remember what it is offhand.
Okay.
So I could look it up this minute if you want to hang on for a second.